Now we're going to talk about aldehyde as well as ketone functional groups. So we'll start with aldehyde. This is a functional group where a single oxygen is included onto your carbon chain, but the structure is a little bit different. This has some R group, whatever it is, to a carbon, double bond to oxygen, and that carbon to a hydrogen. This is the aldehyde functional group. It must be a carbon, double bonded oxygen, and a hydrogen. This means it can only ever be at the end of a chain. If it was in the middle, then that hydrogen would have to be another carbon. And we'll talk about those. Those are ketones. Aldehydes are always a carbon double bond oxygen on the end of a chain where the carbon goes to a hydrogen. The suffix for an aldehyde is al, al. So you got to watch the difference. Alcohols were all, OLs. Aldehydes are al, ALs. Got to emphasize your vowels. But we named them similar to how we did every other functional group. If I have two carbons in a line, and there's a double bond to oxygen and a hydrogen. So this is CH3 to a carbon, double bond oxygen to a hydrogen. So important thing with double bonds, now that we're introducing them to heteroatoms, remember that is two bonds between the same two atoms. That is a single carbon and a single oxygen. There's just two bonds between them. Occasionally folks will think that there's two carbons that the oxygen is attached to, but that is a single carbon. Well, we have a two carbon chain and a double bond oxygen. Generally, in this case, you'll notice I wrote the hydrogen that's on that carbon. Because the functional group of aldehyde itself requires that hydrogen, it is usually written in for clarity. It's not that you can't find it written like that real fast, but in general, you will find it with the hydrogen attached, just so it's super clear you are showing an aldehyde. So all of these are the same thing. These are all two carbons with an aldehyde at the end. If we want to name it, well, it's two carbons. So F for 2. So I have my carbon chain length. I'm going to need my ANE, ENE, YNE. I need my carbon situation. And then I'm going to need my functional group. Well, in our case, my carbons are all single bonded to each other. The fact that there is a double bond to the oxygens, well, that's not double bonds between carbons. The alkane, alkene, alkyne cares about carbon-carbon bonds. So all my carbon-carbons are single, so this is an AN. Remember, we drop the E when we add our other functional group. And so this is an FN al. So written nicely, FN al. Technically it's an FN1 al, but again, that's whenever you run into a situation where there's no option but for the number to be that, we often leave it out. But FN1 al or ethanal is the appropriate name for this. And so any carbon chain that we have, I can have an aldehyde on the end. I can say, hey, here's 3 long with an aldehyde. That is a prop. 3 carbons. 1, 2, 3. And they're all single bonded. Propan. 1 al. Or propanal. Since aldehydes always have to be at the end of the chain, they are universally number 1. If you have a chain, well, you can't have an aldehyde if you don't. So it always has to be 1. So you almost won't ever see the 1 written. It's almost always just prop and al. They have to be at position 1. Exceptions for that would be, well, let's say I had 2 aldehydes. Now, if you watch the alcohols, we didn't show what happened if you had multiple alcohols, but you can have multiple of a functional group. There's no reason you can't. Just like we had multiple subgroups. If you had 2 methyls, you called it dimethyl. If I have 2 aldehydes, it is dial. I just have to include the di. So this is a 4-carbon molecule in our chain. But now numbers are very important because they're not all at position 1. So either side can be position 1. Right? So 1 and 4, no matter how I number it, it's 1 and 4 that's going to get the aldehydes. So the numbering will be the same, but this is 4 carbons, so it is a bute. The carbons are all single bonded, so it's a butane. And there are 2 aldehydes, so it is dash 1,4 dial. It's important that it's dial, not dial. 1,4 dial. And so we can name the aldehyde functional groups. They just go right on the end of the molecule. And if we have numbers to put on, we attach the numbers to them. You won't have things like cycloaldehydes because a cyclic group doesn't have an end of the chain. Aldehydes go at end of chains. And so they will never show up on a cyclic system. Well, let's focus on this molecule here. Except let's do 4 carbons. And what happens if we put our double bond oxygen, say, in the middle? The problem is, if we write this out, I've got CH3 to a carbon double bond oxygen to a carbon double bond oxygen to a CH3. Make that look a little cleaner. Problem is, these carbons, they don't have a hydrogen coming off of them. So you can make a double bond oxygen to a carbon in the middle, but it is not an aldehyde. These are ketones. A ketone has the generic formula R carbon, double bond oxygen, R. In this case, those R's have to be carbon with some kind of carbon hydrogens coming off them. But the idea is they're not hydrogen. That carbon is in the middle of a chain somewhere. It is not at the ends. And that's really the difference in terms of positioning. But that makes a huge difference in behaviors. Ketones are remarkably stable. But an aldehyde, if you left a bottle of aldehyde open overnight and came back in the morning, it wouldn't be aldehyde anymore. Having that double bond on the end makes it significantly less stable and more reactive. So we gave them different names to highlight their very different behaviors. A ketone has the suffix one, own, not one, own. So if we wanted to try to name our starting molecule over here, well, it's 4 carbons long, so it's a bute. All the carbons are single bonded to each other, so it is a butane. And it has, well, in this case, 2 ketones. In terms of numbering, we'd have to say 1, 2, 3, 4, or 1, 2, 3, 4. Either direction, the 2 and the 3 will have our functional group. So there's a butane 2,3 dione. If we want to do a few simpler ones, let's do just 3 in a row. Let's see if you guys can give them a shot. I'll draw a couple. Go ahead and pause See if you can name them, and then come back and we'll give it a shot as a group. Do these two. Go ahead and pause and come on back. All right. If you gave it a shot, let's look at our first one over here. In this case, I have 3 carbons in a line. So this is a prop. And they're all single bonded between carbons, so it is a propan. And there is a carbon 1, carbon 2, carbon 3. Either direction you get carbon 2 is a propan 2-one. Since it can't be on the 1 and 3 and still be a ketone, commonly this is propanone. Like I said, if they have nowhere it could possibly go except that specific number, we often leave the number off. We won't see that in the next one, though. I have a ring. It is 6 carbons, so it is a cyclohex. So cyclo for ring, hex for 6. Single bonds between all the carbons, cyclohexane. And then I have 2 ketones. Well, I have to pick some numbering. Whichever one I number for 1, I can go to the other one for 3. So 1, 2, 3, or 1, 2, 3. Either direction, it's going to be 1 and 3. So this is a cyclohexane 1,3-dione. And so aldehydes and ketones, it's really 2 new functional groups, but built the same way. They are a double bond between carbon and oxygen, where if it's on the end of a chain, so the carbon goes to a hydrogen, we have an aldehyde. And if it is in the middle of a chain somewhere where the carbon goes to other carbons, then we are a ketone. All right, well, that will conclude our aldehyde and ketone component.